Okay, so in today's lecture, we will start with the probability. Do you see the screen? It's PowerPoint screen.
Yes, we do.
Okay. So the learning objectives for today's lecture are to define the random experiments and what are probability, what are the main rules of probability, and we are going to distinguish dependent and independent events. And at the end, we will calculate some probabilities using contingency tables. So what is a random experiment? Okay, so to describe a sample space of a random experiment, a random experiment is an observational process whose results cannot be known in advance. So it's called random experiment. We will start this experiment and we don't know what will be the outcome of this experiment in advance. Of course, if we are going to roll a dice or flip a coin, we don't know in advance if we are flipping a coin. Any coin has two faces, tail and head. So when we flip the coin, we don't know in advance the outcome would be the tail or the head. So this is called a random experiment because we don't know the outcome or the result of our experiment in advance. The set of all possible outcomes is called the sample space. So in the case of flipping the coin, the set of all the set of all the outcomes, all possible outcomes is called the sample space. So sample space in flipping the coin would contain head and tail. It contains all the possible outcome. Okay, and we call it S, the sample space. So here, for example, to describe or to consider the sample space for a single roll of a die. If we want to roll a die, the sample space is, the die, the zahr that we play with. It has 6 faces. Either it's number 1, 2, 3, 4, 5, and 6. So when we roll a die, it's again a random experiment because we don't know the outcome in advance. We don't know which number of these would appear at the end of the experiment. So here the sample space, which contains all the output and the results of rolling the die, it's either 1 or the face that holds number 2 or the number 3 or 4 or 5 or 6. So we have here 1, 2, 3, 4, 5, 6 possible outcomes. All of them are included in what is called a sample space. And of course, if we have, instead of 1 die, we have 2 dice. In this case, we have 36 possible outcomes. It's the intersection between each number of these. So both of the dice may appear number 1 on them, or one of them may appear number 1 and the second number 2, and so on. We have here 36 probabilities or outcomes that are possible to appear as the outcome of this random experiment. The random experiment in this case is rolling 2 dice. So This is if we have, of course, here in the sample space, we have discrete numbers. We have we can't have 1.5. We only have the discrete number 1, 2, 3, 4, 5, and 6. So here the sample space is discrete or is finite. We know it in advance. But what if the sample space is a continuous measurement? For example, if we are considering the time, what is the time you are going to spend in the doctor clinic or at the doctor's clinic? Okay, so in this case, time may be 1 hour 30 minutes and 20 seconds, for example. So in this case, it's not discrete, it's continuous. So the difference between discrete and continuous: discrete are whole numbers with no decimals or fractions, but continuous have fractions. Of course, this is considered as half an hour, so it's a fraction or decimals. So in this case, the sample space cannot be listed because we have infinite number of outcomes, possible outcomes that can be included in the sample space. So in this case, we can describe it by words. So here, for example, if the length of any doctor visit or something like this is considered, in this case, we will say that the sample space in this case will equal all x. X here refers to the outcomes, okay, all possible outcomes such that x greater than 0. Or if we want to write the sample space to describe randomly chosen students' GPA. GPA here means the grade, it's a sum of the grading scale, okay, related to the credit hour system. So we would consider that all x, all the outcomes such that the grade is larger than or equal to 0 and less than or equal to 4. Here 0, of course, no student can get negative grade, is impossible. Okay, so this is why we started at 0. And this is the maximum allowed grade for the GPA. It's like 100 in the normal grading scale. So if we are considering the GPA, the maximum number is 4. So it's again impossible to have any x greater than 4 because this is 4 is the maximum limit for the GPA. Okay, so in continuous sample space we cannot describe or mention all the possible outcomes in a definite way like we did in rolling a die, but we can mention it as this, like this. We can put the limits of the grades, the outcomes, the minimum limit and the maximum limit. Okay, here of course it's greater than 0 because it doesn't make sense that the waiting time, for example, in a clinic or at the bank waiting for your turn to in the cash counter, so it doesn't make any sense that the time would be 0. It's always will be greater than 0. Maybe it's 1 minute, or it may be 1 hour, or if this is so fast, it may be 30 seconds. At any option of these, it's definitely greater than 0. So here inside the sample space, we have each element inside the sample space, we call it an event. So if we want to apply this, we can say that the outcomes of rolling a die, each one of them is considered as an event. Each outcome is considered as an event. The sample event or elementary event is the single outcome. Okay, so if we have that here we call this as a simple event because it only considers one single outcome. Okay, sometimes we want to check the probability. This would be the probability of rolling x equals 1 if the dice will reveal number 1. Okay, sometimes we want to check the probabilities that x equals 1 or 2 or 3. So here we have a complex or compound event as it contains more than one event. In this case, we consider 1, 2, and 3. So here we consider more than one event. Okay, anyone has question? Okay.
اهلا دكتور، السلام عليكم.
Yes, عليكم السلام.
سامحيني ان انا اتاخرت في الدخول بس كان عندي مشكله في الانترنت.
معلش يا خالد.
اوكي، لو بس حضرتك تديني بريف كده سريع عن اللي فاتني.
اللي فاتك we have just started. Okay, I'm recording the lecture. You can follow up. We just started by defining what is the sample space. We are talking about the probability. We say that there is something called random experiment. If we want to maybe roll a die like this or flip a coin, we don't know the outcome in advance. This is why it's called the random experiment. Okay, and we define the sample space. The sample space is the space that contains all possible outcomes. Okay, so here in the sample space, as I've just was saying that each element inside the sample space is called a simple event or an elementary event. Okay, here continuing to the definitions, we have what is called the probability. Probability is a measure for the likelihood. Okay, so the probability of an event is the number that measures the relative likelihood that an event will occur. So here we said that again we have the sample space for rolling a die. This sample space contains 6 possible outcomes or 6 events. Okay, that each number of these represent the number of circles on one of the faces on the dice. Okay, I'd like to share here something with you. So here, do you see this? Do you see my my screen now? It's holding some website. Do you see the website or not?
قدامي probability.
It is the same PowerPoint. I want to show you this. Do you see now the website?
Now we do.
Okay, so this website offers us the possibility of rolling a die. Okay, so each time I would click on this button, I will get a random result of one of the 6. We said there is 6 possible random results from 1 to 6. Okay, so what do you think would be the probability of getting number 6 while rolling the die? What would be the probability? We have here 6. If I hit this button again, what would be the probability that I would obtain number 2? Okay. Oh my God. Okay. What's the probability of getting number 4? Okay. It's random. As we said, it's again number 6. So each time we hit the die, we don't know what would be the outcome. Okay, so we want to measure the likelihood. We want to measure the likelihood of getting number 3, maybe number 4, number 5 in each time rolling this die. Okay, so what would be the probability? What do you think would be the probability in this case? It's a question.
1 for 6.
1
from 6.
1 from 6. This is the probability. This would be the outcome. Okay. What is the probability? The probability would be we have here how many outcomes? 6 outcomes, right or wrong? As it's a fair die and this is a random experiment, so all of them are equal likely to appear in the output. All of them. Okay, so here the probability that x equals 1, in this case it will equal 1 over 6. The probability of x equals 2 equals also 1 over 6. If we repeat this till the probability that x here means the outcome of the experiment equals 6. In this case, the probability again is 1 over 6. So we count the total number of the total outcomes. We have 6 possible outcomes. And each event is a single one. So we divide 1 by 6, 1 by 6, 1 by 6. This is the probability for getting each one of these numbers. Okay, so if we add the probability of these all outcomes of the whole sample space, we'll get what? 1 over 6 plus 1 over 6 okay, equals what? In this case, equals what?
1, 1, 1, 1.
6 over 6, which equals to 1. Okay, so this would be the maximum probability in case we have the outcome equals all the sample space. Okay, x equals the whole sample space. In this case, the maximum probability equals 1. So what is the lowest probability? So if I am rolling a die, okay, and one of my rolls, I bet that I will get 1. Instead, I get 2. So in this case, the probability of getting the one was what?
Sorry, doctor, repeat question.
The question. If I'm telling you, I think the next time I will hit this button, I get 1, okay? And I got any other number than 1. So the probability of x equals 1 in this case equals what? In this specific case.
1/6.
No, I didn't get the 1. I get other outcome. Equals 0. I didn't get the 1. I get other thing. Okay. So here the minimal probability would be 0, and the maximum will be 1. So any probability of any outcome, this is a general rule for any probability. It's between 0 and 1. It can't be greater than 1. This can't be, and it can't be less than 0. What's the meaning of the probability of getting 1 is 0? It doesn't mean is -1. It doesn't mean anything. Okay, we want to get a number that is between 0 and 1. Of course, if it's very close to 0, in this case, its likelihood is very small. Its likelihood to happen or to occur is very small, and if the probability is very close to 1, in this case the probability of obtaining this outcome is very high. Okay, is this okay with all of you or not?
Yes, it's okay.
Okay, anyone get confused at any step, just stop me. Okay, so if I want to apply this on the head and tail, what is the sample space of flipping a coin? It's a question for you. What is the sample space of flipping a coin?
هتكون 1 and 2.
What? S equals
1, 2.
Head or tail. Okay, so
أو يعني
do not be
2
confused. So what is the probability of getting head and what is the probability of getting tail?
It's 1 to 2.
1 divided by 2. We have 2 possible outcomes. Okay, so here again we would assume that it's a fair coin. Fair here, it means that no face is weighs more than the other, or any cheating happens during the flipping process. It's a random process. So in this case, the expected probability for getting head is half, and the expected probability for getting tail is again half. Okay, so again, if we have the sample space of here, the probability of the whole sample space, if we are considering the case of flip a coin, okay, so the probability of the sample space will be the probability of the first event, which is the probability of getting head, plus the probability of getting a tail. So in this case, it equals to half plus half equals 2 divided by 2, or equals 1. Okay, why it's 1? Because it's the probability that it's the more logical that if we have a coin that holds only 2 faces, okay, It's either the tail or the head. What's the probability that I will get head and tail, the whole sample space? It's 1. There is no probability of getting something else. Okay. And of course, if we continue this for the same example of rolling a die, so we have here the probability of getting 1 or probability of getting 2 till the addition of the probability of getting 6. In this case, each one equals 1 divided by 6. Okay, and it will equal 6 divided by 6 or 1. So if we have a sample space and we want to calculate the probability of the whole sample space, in this case, it will be the summation of the individual events, the probability of the individual events, and in this case, it will add sum up to 1. Okay. So now again we said the probability is the measure of the likelihood of some outcome or some event. Okay, we have 3 types of probability. Either it's empirical. In empirical probability, I observe the outcome of the experiment. So here, while I am considering rolling a die, so each time I hit the button, I will register that the obtained outcome. So maybe sometimes it appeared 6, then 6 again, then 2, then 4, then 5, and so on. Okay, each time one of them appears, so here the probability of x equals 6 would equal 1 over 6. The probability of x equals 6 equals again 1 over 6. So at the end of the experiment, I will see what was the probability that x equals 6. Maybe it equals 6 for 3 times. So in this case, due to my observation, the empirical probability revealed that 6 was repeated 3 times. So the probability of getting 6 was 3 divided by 6. Okay, so this is what is meant by empirical. It's basing on the observation. Okay, the second type of probability is called the classical, and here by classical we mean what is the assumed probability, for example, or what is the priori. We know it in advance. How we know it in advance? As we said that as it's a free experiment and it's random and the die was fair, so the probability of getting 1 would equal to the probability of equal 2, and the probability of getting 3 till the probability of getting 6. All of them would equal 1 divided by 6. This is called the classical probability, as we previously know that the result of 1 would be 1 divided by 6. I don't have to roll because it's a previous or it's priori known information for me. Here, for example, if we are rolling or flipping a coin with head and tail, 2 faces, I know that before flipping the coin, if I am betting my money that the result will be head, I know that there is a 50% chance that I will lose my money and 50% chance that I will gain the bet. Okay. The third type of probability is called subjective. Subjective here means dati. Okay, It's something that is not objective. It's not built upon science or assumption or hypothesis or something like this. It's based on my personal opinion or judgment. So if I ask you a question like, what do you think the probability of spreading coronavirus in the next week? Okay, some doctors may say it's 20%. Someone, according to his opinion, if he is optimistic, he would say that I think it will be 10%. وهيحصل انحسار ومفيش انتشار. So in this case it will be 10%. Other one would say, according to my previous readings, the probability of spreading, I think, compared with what happened in SARS and so on, I think it will be 30%. So the all answers was, I think it is so and so. In this case, the estimated probability is based on a personal opinion or a personal judgment. Okay. So I have a question for you. If I have asked this question and someone, instead of saying this, he said the spread in USA last week was 25%. So I think that it will be 25%. Is this, what is the type of this probability? It's a question.
Subjective.
Subject.
Subjective?
It's a subjective.
No, subjective. Empirical.
Empirical, excellent. Why empirical?
Because there is a similar percentage for the probability.
It's based on a previous observation of what happened in the last week in USA. So it's not subjective. I am building my estimation upon something had been observed before in another country. So in this case, it's empirical. Okay, I'm basing my estimation upon some previously observed outcome or frequency happened in another country. Okay. Also, if I am saying that what happened in SARS, that the spread in the fourth week was 10%. So in this case, I think it will be 10%. In this case, it's also empirical because it's based on some observation. Okay. Subjective is not based at all at any measurement. It's according to my estimation, my belief, my opinion. Okay, if it depends on the someone if he is optimistic or not. Okay, so these slides, of course, I upload the detailed slides for you in order to study them on the Moodle. Okay. So these slides have the same what we have said about the empirical and the other types. Okay. We have here a very important concept in probability known as the law of large numbers. What's the law of large numbers? This law states that as the number of trials increases, any empirical probability approaches its theoretical limit. Okay, we can check this. We can change this. How? I'm going to go here again. Okay, and I will flip this coin. Okay, so again it's random experiment, and the space, the sample space contains only head or tail. Okay, so I'm asking you, please, in your notebook, register the outcomes of the following 10 flipping I'm going to do. Okay, if it's head, just write H. If it's tail, write T, and we will count what was the total output if we flip this coin 10 times. Okay, I will start. It's T, T again, head, 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 T, T, head, T, and T. Okay, so how many T have we got and how many H's?
6T و4 H.
6T and 4H.
6T and 4 head. So if we divide 6 by 10 and 4 by 10, because this is the total number of experiments we did, we get that the probability for the T is 0.6 and the probability for the heads is 0.4. Okay, this is of course an example of which type of probability? Observational or empirical or subjective? Hello?
I think there is classical.
No, it's observational. We did the experiment and we write down the results of this experiment. It's total application of the observational probability. Okay, so here we run the random experiment, we register the outcomes, and in this case we observed all the outcomes, and it's called observational probability. So the observational probability is 0.6 and 0.4. The classical probability is 0.5 and 0.5. Okay, it's a classical. Okay, we know that there is only 2 possible outcomes. Okay, so the probability of rolling or flipping a coin for 10 times revealed that 0.6 for the tails and 0.4 for the heads. If we are going to do the same, okay, but I'm going to do another 10 flipping for the head and the tail, and I want to consider the total number of the outcomes. Okay, so this time instead of dividing by 10, you would divide by 20. Okay, I will add another 2 trials. Okay, so let's start. I will start with the first one. It's head, tail, head, tail, tail, head, tail, 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 tail. So what's the result of these extra 10 trials?
The probability of tails, it's 0.7 and the head 0.3.
0.3. You divide it by 10 or by the 20?
لا by 10.
لا, I want the result of the 20 trials. The whole بقى the 10 plus the 10. So in this case, you have got حد عنده بغبغان ولا ايه؟ All this time is needed to calculate the probability out of 20? So Sandra Nabil didn't attend, and Rami and Ali, though I thought I saw him at the beginning of the lecture. Who else? Hajar and Habiba attending, Khalid, Sandra, Adel, and Sarah, and Gasser. Who didn't attend? 1, 2, 3, 4, 5, 6. There are 4 absent. Sandra, Nabil, Rami, Ali. Who's the 4th? I will check.
Yamin.
Yamin, yes. And I think he didn't attend also last time. Yes, Yamin didn't attend last time also. Has he attended at the morning?
No. Yamin is not attended today.
لا جه واحد ليكتشر واحدة بس اللي هي كانت الأول.
Okay. So what's the result? All of this time is wasted to calculate the output out of 20 experiments. What's the problem? Hello?
Hey, doctor.
What's the problem? If we have 20 trials, what is the probability of the tail and what is the probability of the head?
هتبقى 7 over 20.
7 over 20 or خالد ركز معايا. The result of the second 10 results was what?
0.6, 0.4.
This is when we drawn the 10 trials, right or wrong?
Yes.
طيب
Yes, yes,
the
yes.
second 10
yes, 0.2 and 0.8. 1.2 and 0.8.
0.2 for which one?
Not 0.2, not 0.2. If there is the coins will be movement similar for the 10 terms, the T probability of T equal 1.2.
ازاي 1 اذا كان لسه قايله ال probability cannot exceed 1.
1 اسف maximum 1. Yes, yes, maximum 1.
طيب forget it's 20. Okay, what was the result of flipping the coin for extra 10 trials, and where are the rest of the students? I'm seeing only Khalid is participating with me. Where is Hajar and Habiba?
هو انا الصراحه بحاول اجمع بالظبط انتوا بتكالكليتوا ازاي، بس مش قادره اعرف.
طيب
أنا I lost
calculate
track. التاني ترايل كان طلع 2 over 8، فمثلا يعني 2 أو
ازاي 2
2
over 8 ازاي بس 2 over 8 to be يعني to be clear, we usually divide by the total. Okay, so here we have 10 trials, so this is why we divide by 10. Okay, we have 6 outcomes out of 10 that said that the tail, the output was the tail or the head, I can't remember. It was the tail or the head?
The tail.
The tail. Okay, so 6 times out of the 10 we have got the tail. So in this case the probability of getting the tail equals 6 divided by 10. Okay,
أنا أقصد بقى the
4.6.
second trial did we got 2 tails and 8 heads?
In the second 10 trials you get what? 2
tails and
tails.
8 heads.
Okay, so if we are calculating again divided by 10, let's call it by 10, we have
2 over
2 tails, and the probability of having head is 8 divided by 10. Okay,
So we add the tails with the tails, يعني 0.6 plus 0.2.
يعني if we can say that, forget that we did 10 and 10, if we are doing 20 experiments, okay, what would be the total numbers that the tail appeared here? It's the 6 plus 2, it will equal to 8, and here it's what? 4 plus 8, it will equal to how much? 12. Okay, the purpose of doing this is what? Here we found that the probabilities were 0.4 and 0.6. If we increase the trial, so if instead of doing only just the trials, we do 20, after that we do 30, 40, and 50, as long as we are going to increase the number of trials, the observed probability will approach what? The empirical probability. So here, for example, forget about the 20. Forget about this. The output was 2 divided by 10 and 8 divided by 10. So it's 0.2 and 0.8 if it's 10 drawing. Okay, this results are far away from 0.5. We said if we drawing or if we flipping a coin, we have 50% chance to get head and 50% chance to get tail. This is the empirical, this is the classical
Classic.
probability. I said the empirical. No, this is the classical. Okay.
No.
So here, if we increase the number of trials we are hitting the button in order to check what would be the outcome, is it a head or tail? If we do this trial for 50 or for 100 times, in this case, the observed or the empirical probability obtained from the observation will be very close to the classical probability. Okay, so to understand this, we have this graphical representation that shows the output of flipping the coin for only 10 times. Okay, here the red line refers to the probability of 0.5, which is the classical probability. This is the red line. We can see that in the first outcome, their probabilities are different, and as long as we are increasing the number of trials, the number of hitting the button in order to check, the output will be a head or a tail. Each time we increase the number of the trials, the probability approaches what the observed probability. The blue here refers to the observed or the empirical probability, and the red is the 0.5, the classical probability. So each time we do more experiments, at the end of these experiments, we find that what the empirical or the observed probability will reach the classical probability. Okay.
هو يا دكتور انا مش فاهمه الحته دي، يعني مش فاهمه يعني ايه الامبيريكال يوصل للكلاسيكال، مش قادره استوعبها برضه.
empirical الاوتبوت اللي بيطلع لك if you really flip the coin. Okay, you are holding a coin right now. احنا الكلاسيكال it's a priori. احنا we are assumed that in the classical probability that as the coin has only two faces، فده الاوتبوت هيبقى ايه؟ يا اما tail يا اما head. It can be anything else. It can be empty. مش هيطلع لي حاجه empty. مش هيطلع لي حاجه third face. Okay, it's only one of the two faces would appear. خلاص. So as I know this information previously that I only have one of the two outcomes, in this case I know that it will be a head or it will be a tail. So this is called a classical probability because I know the result in advance. I know the result مش بتاعت الاكسبيرمنت. I don't know اللي هيطلع head ولا face ولا tail. I know the probability. I know that it's a 50% chance that it will be a tail or a 50% chance it will be a head. I know the probability, the likelihood, okay, the possibility that it will be either a head with 50% chance or a tail with 50% chance. This is called the classical probability. خلاص؟ الempirical, anything empirical دايما بيبقى related to experiment. حاجة empirical، حاجة practical اتعملت. Okay, so here empirical, it's an example of opening the website as I have just did, and I tell you I will hit the button for 10 times and please count the number of heads, okay, and the number of tails. ففي الحالة دي احنا مش خلاص احنا know the classical it's 50-50. Okay, it's 0.5%. إنما if I am doing the experiment right now, I would like to know، أنا مش عارفة اللي هيطلع head ولا tail، فلما نكررها 10 مرات I would see from out of the 10 trials how many time I will get the head. Out of the 10 trials how many time I will get the tail. فبحسب عدد المرات اللي طلع لي فيها head على ال 10 وعدد المرات اللي طلع لي فيها التيل على ال 10 واي كومبير بقى في الحاله ديت هو التيل كانت البروبابيلتي بتاعتها 0.3 مثلا والهيد 0.7. okay so this is different from the classical probability. Classical probability assume ان دايما انت you have 50% chance to get one of them. But what happen in the real life while you empirically apply a random experiment, you will observe different results. Okay, so this is called an empirical probability. Have you got it?
اوكي تمام، بس اللي برضو اللي بسأل فيه يعني ايه بتوصل للكلاسيكال؟
يعني ايه بتوصل للكلاسيكال؟ طيب the result of the 10 trials one of the results was 0.6 و 0.4 والother 10 again كانوا 0.2 0.8. طب لو أنا عملتها instead of counting the number of heads and tails out of 10 trials لا out of 100 trials how many the number of heads and how many the number of tails appear. كل ما هنزود عدد الترايلز the empirical, the observed probability will be very close to 0.5 and 0.5 will be very close to the classical probability, the assumed one. Okay.
اوكي طيب يعني لحد
This
ما
is
جمعتها.
called, yes, this is called the rule of large number. Here it's meant by large number if you apply the trial, the random experiment for large number. In this case, at the end of the large numbers, you will find that the empirical probability would approach the real probability, the classical probability. خلاص يبقى انت فكري فيها كده. انت هنا احنا كان بيطلع لنا مثلا 6 من ال10 مرات. طب out of 100 it will be very close مثلا ل 55 divided by 100. تمام. ف it's really approaching ال 0.5. okay here and here. طب out of 200 it may be very very close بقى to ال 0.5. okay and so on. okay
اوكي
طبعا دي
تمام.
multiplied بقى في يعني دي هتبقى 102 ودي هتبقى 98 over 200. okay okay these are just examples to calculate the this is an example for the classical approach. okay as I'm telling you classical approach that what things that should be. okay but when you are conducting a random experiment the outcome may be different than this. I told you if I am rolling a dice the outcome or the probability of each one of the outcomes would equal to 1 over 6. This is called the classical probability. okay this is what we know in advance. This is the priori probability. okay but if I am started to really roll the die like this one, okay, like we had here in virtual die, okay. So if I start to hit here, it's a 5. So please write down 5, okay. The second hit will give us again 5. The third time give us 2, 3, 6, 4, 2, 2 again, 4, 3, and 5, okay. So please concentrate with me right now, okay. طيب, how many trial have we did? It's a question for you. We did 10 trials, right or wrong?
10 ولا 11
wrong 11.
11 تقريبا.
11.
طيب
11
اشطبوا على اخر واحده، اشطبوا على اخر واحده، اوكي.
مم.
طيب according to، خلوا بالكم قوي بقى من الجزء اللي هقوله ده. according to the observed or the empirical outcome, what was the probability of 1?
1/6 1/10.
طلعت مره 1، طلعت مره
لا ما طلعتش ولا مرة.
يبقى it's 0.
اوكي
probability of 2
3.
3.
3/10.
مم.
Okay, so and here probability of 3
3
مرة
1
مرتين
2.
مرتين.
مم.
probability of 4
2
مرة
2.
لا 2 برضه 2.
2
probability of 5
2
مرتين
5. 2.
probability of 6
مرة
1.
مرة. Okay, so it's 0.1. طبعا of course if we add all these numbers we'll get the number 1, okay, as this is the output of all our trials, okay. 3.5 0.33 plus 0.2 it's 0.5 plus 0.2 0.7 plus 0.2 it's 0.9 and plus 0.1 it's 1, okay. طيب according بقى this is called the empirical or observed probability, okay, because we observe it during our random experiment. طب according للclassical probability كان المفروض ال P equal 1 بتساوي كام؟ 1 divided 6, right or wrong? It's not 0, okay. This is why we call it classical, because this is the assumed probability before conducting the random experiment, okay. This is the assumed value before running the random experiment, okay. Probability of what? Of 0.2, it's not supposed to be repeated except it's only repeated for 1 time, okay. But here it's repeated for 3 times. If we conduct this experiment for more than 1 time, you will find the probability of this would be different than the probability of this. So this is called the classical probability. It's the previously assumed probability. Okay, we are assuming that all of them will be equally likely. The output or the outcome of the experiment should be equal to the outcome of 2 and 3 and the rest of the 6 numbers. Okay, but this is what happened in the real world. In the real world, that we find that 2 is repeated 3 times, 3 was repeated 2 times, and so on. Okay, so this is the difference between empirical or observed probability and the classical probability. Okay, so for this example, I won't solve this example because it's already solved in front of you. I want to know what is the probability right now. And in this case, it's a classical. Why it's a classical? Because it's included in, we call this Venn diagram. Okay, Venn diagram. I want to calculate the classical probability of obtaining 8. Outcome equal 8. Of course, this is rolling 2 dice. It's not 1. So it's possible to have number 8 as a result. I want you to calculate what is the probability that the outcome would equal to number 8. You have 10 seconds. حد يعمل صوت، يحسسني انه بيحسب حاجة، عشان يعني it's really boring.
يعني they need to add up to 8.
What?
التو الدايس مع بعض
Yes, the
summation.
2 dice, the summation of the faces on the 2 dice will give us 8.
Okay.
هي دي المفروض نحسبها ازاي؟
هتحسبيها ازاي؟ How do you propose
يعني من الجيفن اللي فيه الفاليوز اللي موجودة ولا؟
من ايه؟ من
5 by 36.
طيب, we said before we have 36 possible outcomes if we have 2 dice. صح ولا لأ؟ So we usually, to calculate the probability, we divide by the total number of the possible outcomes. It's 36. So we agree about the denominator. Now we want to identify what would be the numerator. Okay? So here inside the Venn diagram, it gives us the all possible combination between the 2 dice. Okay? So
5 by 36.
حاضر يا خالد عشان الناس اللي they don't understand. Okay? So here we have all the combination that would give me the result of 8. Where I will search for these results, I will find this first one. One of the die, the face will have 2 and the second have 6. So the summation of the 2 dice will be 8. Okay, and I will go here searching for 8. I find this again. 3 and 5 equals 8. Okay, I go down here. I would have 4 and 4. Okay, here I have another 5 and 3. Okay, and here I would have 6 and 2. So here I would have how many possible outcomes if the first die has 2 and the second has 6. The first have 3 and the second has 5. The first have 4 and the second have 4. The first have 3 and the second have 5 and the second have 3. If the first have 6 and the second have 5. To count these possible outcomes, we have 1, 2, 3, 4, 5. So we would divide 5 by 36. This is the probability of getting outcome equals to 8. And this is called the classical probability. Why it's a classical? Because it's drawn upon the assumption of what would happen if we roll the 2 dice. Okay, it's not based on a real observation like this. Okay, it's not based on really rolling the 2 dice and watch what would be the outcome. All of you are following?
Yes, doctor.
Okay. So and at the end it's talked again about the subjective probability. Okay, so here we have very important rules regarding the probability. Okay, one should be always in your mind that probability always cannot exceed 1 and cannot be less than 0. So probability always is contained within the range 0 and 1, and of course 0 is included. It can be equal 0, as we have watched in the empirical probability. The probability of getting 1 was 0. 1 doesn't appear in the random experiment, and we have the probability of 1 if we have definite probability, such as calculating the probability of the whole sample space. In this case, the probability would equal to 1. So this rule must be in our mind. We can't exceed 1, we can't be less than 0. Okay, we have here a second rule, and it says that there is something called the complement of an event. To understand what's the complement of an event, let's consider that we have an event called A, and this event contains the outcomes that of the rolls will be 1 and 2. So we said the sample space contains from 1 to 6. For this event, we have something called a complement event, or A prime. It will contain all what is not included in A. So here, what is not included in A will be 3, 4, 5, and 6. Okay? Okay or not?
Okay.
Okay. We said that the probability of getting the whole sample space is simply 1, and this is logic. The probability of getting the whole outcomes will be 1. Okay, it's the addition of the outcome of the individual events, and in this case we get 1. Okay, so here, as A complement or A prime contains what is not included in A, so if we add A plus A prime, we'll get what? If I add A and A prime, I will get
SS.
Excellent. Okay, so here the probability of A plus the probability of its complement equals what? Probability of S, which equals what? 1. So
6 from 1 to 6.
no, the probability of S equals 1. The probability of S, the whole sample space, equals 1. Okay? So if I have the probability of A and I don't know the probability of A complement, can I calculate it? Yes, I can. How
Yes.
is that?
Yes.
By saying the probability of A prime equals 1 negative
Minus.
the probability of A. Excellent guess. Okay, so each one would equal the probability of others. So this is why, because it's very important for me, you have to understand. I don't need you to memorize. If you understand, you don't have to memorize. Okay, so here this shows you a diagram of the sample space. Shows you that this is the compound event A, or a single, even if it's a single event A, and the complementary, the set that contains all what is not included in A. Of course, both of them will shape my whole sample space. So if I'm adding the probability of getting A plus the probability of getting A prime, it gives me 1, because it's the probability of getting the whole sample space. If I have one of them, I can calculate the other by simply subtracting it from 1. Okay? So this is considered as the second rule. Let's talk about the third. Okay? We have union of two events. What we mean by union? We mean that if we have event A and event B, and I want to calculate what is the probability of getting B or A. We can write it in symbols like this, P or A, okay? And we call it the union of the two events, okay? So here, if we have two events like this, they are intersecting in this area, okay? There is an intersection area between A and B. So in order to calculate the probability of A union B, we would say it's the probability of getting A plus the probability of getting B, but you have to be very careful, as these two events are intersecting in this area. So this area is included here, and it's also included here, right or wrong. This is the intersection area between both of them. As I am adding the whole A, including this intersection area or this part inside A, and if I am adding the whole B, including this part of the intersection area, this area would be calculated 2 times. So in order to not calculate it 2 times, we have to subtract this, the probability of this intersection area. Here, this sign, it's called intersection, okay? And this sign is called union, okay? So this explains that contained in both, as I told you, it's contained 2 times in A and B. So to remove this to not be repeated 2 times, I have to subtract the intersection between the 2 events. Okay, in order to find the union of A and B, I add the probability of getting A, and I have the probability of getting B. Again, this area is included in A and B, so I have to remove it in order to not be repeated twice. Okay, so here is an example for this. Okay, if we have a deck of cards, cucina, okay, and it usually contains 52 cards. Okay, so this is an example of calculating the union of 2 events. Okay, so P of Q means that the probability of getting a queen. Q refers to the queen. Okay, so in any deck of cards, we have 4 queens, 2 in red and 2 in black. Okay, and the shape is different between the we differentiate between the 2 red and the 2 black with different shapes. Okay, I think speed, blocks, diamond and hearts. Okay, diamond and hearts are colored in red, and blocks and the speed are colored in black. Okay, so the deck contains four queens, and we have the total number of the whole deck, the total outcomes. As we've said, we usually divide by this total number, it's 52, and the possible outcomes of queen, only 4 cards. This is why the probability of getting a queen equals 4 divided by 52. Okay, there is another probability for getting red cards. Okay, so the probability of red cards, of course, the deck is divided into 2 parts, equal parts, 26 red and 26 black. Okay, and of course the total number again is 52. So to get the probability that we get red cards, it's 26 divided by 52. Okay, so there is intersection between queen and red. The intersection is that 4 of the 2 queen cards are red. 2 of them are red. So we have, as we said, 4 cards, queen, okay, queen cards. 2 of them are red. So this is considered the intersection area, that we have 2 red queens. Okay, so this intersection area can be calculated as the total number again is 52 cards, and we have only 2 cards in red. So if we want to calculate, this is a question for you, if we want to calculate the probability that it's a queen or it's red in 10 seconds, what would be the probability of getting a card, it's queen or red?
There is equal probability of queen plus probability of red minus probability of queen intersection red.
Excellent. So we have to write down the rule, and the rule says that the probability of queen plus the probability of red negative the probability of their intersection. So we just substitute the probability of queen is 4 divided by
0.54
plus 26 divided by 52 negative 2 divided by 52. The result here would be say it's 20 it's 4 negative 2 would give us 2, so it's 28 divided by 52. Okay, this would be the probability. How and the result would be what's the result you said, Sarah?
أنا حبيبة 0.53.
Excellent. It's 0.53. Okay, it's 0.53 like here, or 53. Sometimes they transform it into percentage as it's a chance to say that there is, it's very important to properly interpret your results. So there is about, because this is a really high fraction, there is about 54% chance that we get a card to be queen or red. Okay, and this is a very important result because the probability of getting red, it's 50% to get red, and the 4% refers to the additional amount of getting two cards, okay, of the queen. And of course we have to subtract the intersection between the two events. Okay, so I think this example clarified the concept of the union between two events. Okay, the probability of two events. Okay, there is another case if we have what is called the mutually exclusive event. By mutually exclusive, we mean the two events are disjoint. They are not connected and there is no intersection between them. Okay, so if there is no intersection, in this case we have a special law of addition, because the intersected area equals what? 0. There is no intersection. Okay, the probability of the intersection is 0 because there is no intersection. Phi here means nothing. There is no intersection. A intersection B equals phi. Okay, it doesn't exist any intersection, so the probability of their intersection is 0. This is why this term would disappear from this equation. So to find the intersection, the union of A and B, we just need to sum A and B. We don't have any repeated area in the intersection, so we don't have to subtract anything from this formula. Okay. There is another thing that you must know, that sometimes we have events which are called collectively exhaustive. The collectively exhaustive if the union is the entire sample space. So here if we have for example warranty and no warranty, if you are going to fix your car or something like this, or any electric machine, and the insurance asks you about the warranty, your status will be one of two. Okay, it's either you have warranty or your warranty is finished, or you're out of warranty for any reason. You hired unspecialized labor to fix your car or something like this, so you don't have warranty. So here the sample space in this area, or the addition of the two events, are collectively exhaustive, because their addition or the union of these two sample space will end up with the whole sample space. The union of the two events will end up with the whole sample space. Okay, this may happen if we have binary events. Binary always means two things, okay, like 0 and 1, like male, female. In this case, we have binary events. Also, collectively exhaustive events can occur in the situation we have here more than two events. If we are checking the payment criteria, either the customer can pay using his credit card or debit card, or using cash or check. There is no fourth way. Again, the union of the four events will give us the whole sample space. Okay. Okay. So there is another very important probability definition known as the conditional probability. Okay. So what do we mean by conditional probability? Let me show you that. Okay. We have here, you see my screen, right, or not? It has a deck of cards. Okay. So here, if I start to draw one of the cards, so I got here 5 and it's black, and it's the shape is called the blocks or something like this. Okay, and I have here red queen. So if I am asking you, what is the probability that the next card will be a red queen, given that we have already drawn one red queen? Okay, so again, the question is that we know, let's put this back, we know that we have 52 cards. Okay, if this is turned down like this, we have 52 cards. I don't know what will be the next card if I hit the button. Okay, and I will put money to bet for the next bet here يرهن تمام for the next card, and I want to know what would be the probability of getting a red queen, given that this is the very important, because if we don't have this red queen, in this case the probability of getting red queen, it will be 2 divided by 52, the number of red queens in the deck of cards divided by the total number, so it will be 2 divided by 52. Okay, but here the situation is different. Why is that? Because I have already drawn one of the red queens. So the question is not what's the probability of getting a red queen. No, the question is what is the probability of getting a red queen given that one of the red queens already has been drawn. Okay, this is called a conditional probability. Yes, anyone has any question?
1 divided of 51.
No, it's not that simple. Okay, you will see this. Okay, it's not that straightforward. Okay, so here to calculate it's called a conditional probability and has rules يا جاسر يعني انت عايز تخلص خلاص. Okay, so we have here what is called conditional probability, the probability of an event A given. It's very important to notice this word, okay? Given that event B has occurred, it's already something that happened as in our example, one specific card was drawn. So what is the probability of event A given that B has occurred? This conditional probability is denoted by B of A, event A, given this straight line is called the given B. Okay, the vertical line is read as given. So the rule here is that the probability of A given B equals to the probability of A is intersecting with B divided by the probability of B. Okay, and of course the probability of B is greater than 0 because if this is 0, any division of 0, you know that it will end up with phi or infinity. Okay, so here the conditional probability, in order to be calculated, we have a condition that P is greater than 0. Okay, and of course it's limited with 1 as the case of for any probability. So again, the rule that you must know that probability of A given B would equal to the probability, the intersection of the two events divided by the probability of the second event. Okay. So here it explains the logic behind this rule. As the sample space is restricted to B, okay, that has occurred. So here we are restricting ourselves to the intersection between the two parts, and we put it in terms of like a ratio or relatively what's the probability of the relative probability between getting this intersection, both of them or both of the two events has occurred, given that the probability of B. Okay. So here, of course, as it's written like this, if I can use this cross multiplication, if I have the intersection, or if I have the given probability but I don't know the intersection, for example, so I can say the probability of A intersecting with B would equal to the probability of AB times the probability of B. So we are just rewrite the equation. Both of them are equal and the meaning of both of them is the same. Okay, so here the general rule of multiplication, if we are seeking to know the intersection between the two events, in this case I will multiply the given probability by the probability of B. Okay, so here is an example. If we have a population of people aged from 16 to 21, and they are not in the college. Okay. And after doing a survey, we found that the percent of unemployed people inside this population is 13.5, and the percent of those who drop out the high school is 29.05, and the percentage of unemployed high school dropouts, so they are unemployed high school dropouts. Okay, this is the percent of them. And the question needs to know what is the conditional probability that a member of this population is unemployed, given that, so we want to calculate the probability of unemployed, given that, okay, the person is high school dropout. You solve it. Have you started to solve it? Any response?
Yes.
Yes.
Doctor, is it going to be the union of high school dropout to unemployed?
No, it's directly said
Okay.
and asked you, it needs a conditional probability. It's not a union or something like this. It's you will apply the conditional probability rule. To memorize the conditional probability rule, A given B, okay, will always usually or always will equal to their intersection divided by this one, okay, divided by B, this one. So it's the intersection between the two events divided or relative to the size of the second event.
هتكون 0.18.
What?
Is it going to be 0.18?
0.18. Okay, and the others?
0.18.
1.18.
0.18. أيوة هي كده فعلا.
0.5.
0.18.
0.18.
0.18.
Okay. All of you agree?
Yes.
Okay. So to calculate the probability, as you find that you only have to, here, you only have to write this as these are probabilities, okay? The probability of unemployed equal 0.135, okay? and here the probability of D or high school dropouts 0.2905, and the probability that this is considered as the intersection because they are unemployed and high school dropouts. So this is the intersection probability. It's 0.0532. Okay, excellent, all of you. So here we just apply the rule. It's a probability of unemployed given a dropout of high school. We divide their intersection by the probability of the dropout. So we get that the probability it's 0.18 as you have reached. Okay, and it adds an interpretation. As I told you, it's very important to know how to interpret your results. It's not important only to calculate them, how to get the benefit of these results. So it's indicating that the probability of unemployed, given that they are dropping the high school, it's 0.1831, which is higher than the probability of unemployed. So in this case, there is a relationship between employment and school dropout. So most of the unemployed people are the ones who drop out the high school. Okay. Here we have another definition of the events. We have what is called the independent event. This states that if the probability of A given B equals the probability of A, in this case, we would say that A and B are independent or not dependent. This, of course, means that the information that B is already occurred doesn't affect at all the probability of A to occur. So in this case, the two events are independent, to put it very simply. So again, the probability that B has been occurred doesn't affect at all the probability of A to occur or to happen, or probability of A is not affected. So in this case, there is no relationship between event A and B. If event B has occurred, nothing would change the probability of A to be occurred. Okay, so we say in this case, the two probabilities are independent or are not dependent. Okay. Here, as in the previous example, the probability of U given D doesn't equal the probability of unemployment. Okay, so we can't say that they are not dependent. No, they depend on each other, because given the information that these unemployed people were high school dropouts, changed the probability. Okay, so here we cannot say that. So U and D are not independent, or you can say they are dependent. Okay. Another way to check for the independence between two events is to following the multiplication rule. Okay, if the probability of A intersect B equals the probability of A times the probability of B. So if the intersection between two events equals their multiplication, in this case, we call event A is independent of event B. Both of them are or don't depend on each other. Okay, since they proved why this multiplication rule or law is applied, since the probability of A given B equals the probability of A intersect B divided by B, as they can be multiplied together. In this case, this B will go with this B will equal to the probability of A again. So here we'll go back again to this rule. You don't mind about the proof of getting the rule. You only have to know that to check the independence. Either you will follow this, you will check if the probability of A given B equals the probability of A, or you can calculate this to check if you have given in the problem A intersect B some value, okay, and you have the value for the individual events, the probability for the individual events. You have to multiply the probability of the individual events. If the multiplication gives you the same result of the intersection, in this case they are equal and they are independent of each other. Okay.
دكتور هو معلش هو كان لما كان بيبقى اليو لفوق او الفتحة لفوق كده كان بيبقى ايه؟
يونيون. بس خلي بالك دي مش يو، دي you are talking about which one here.
انا عارف اصل هنا
you
يعني
unemployed ها
كده بتبقى ليها intersection.
if it looks down it's intersection. Okay, if it's up it's a union. Okay, you can memorize it. You see here the U. Okay,
اليو والان بس هو
U and U. If it's U and U, in this case it's a union. Okay, it's or. Okay, in the other direction, if the symbol looks down, in this case it's an intersection.
معلش هو ايه الفرق تاني عشان انا كده مش عارفه ليه اتلخبطت.
الفرق is if you have two events A and B, this area is called the intersection. التقاطع ما بينهم. اوكي، المكان اللي هما الاثنين بيتقابلوا فيه. اوكي.
Okay.
This is called intersection. Okay. The only place the two events are intersecting here. So I'll give you a simple example. If event A equals, if we have these outputs for rolling a die, and for event B we have these outputs. Okay, so event A, it's all the outcomes will be from 1 to 3, and for event B, for example, the odd numbers. Okay, so what is the intersection between A and B?
One or three.
Excellent. 1 and 3. Okay.
Doctor, repeat the question, please, doctor.
اليونيون. طيب.
اليونيون. Okay. If we want to know what is the union, okay, what will be the union here? It's
A plus B
plus B excluding the intersection. ليه؟ لأن إحنا لو قلنا إنها ال A تمام plus ال B, as we said, we will have the events to be repeated. This is wrong. So to have A union B, we will say A plus B negative the intersection between the two of them. So to do this, we will have here what?
هيكون 1 2 3 5.
Huh?
1 2 3 5.
Okay, negative 1 and 3. Okay, so we have here 1 2 3 5. خلاص يبقى الunion you are adding A plus B negative the intersection. Intersection is only the area that is connecting A and B. Okay. خلاص حبيبة.
تمام تمام.
Okay. طيب again what we were talking about the independence. Okay, so here any number of independent events, we will usually have the intersection between these events equal the multiplication of their probability. Okay, the probability of their intersection will equal to the probability of their multiplication. Okay, so this is an example for independent events. If to illustrate system reliability, suppose a website has 2 independent file servers. Each server has 99% reliability. So this is the probability of reliability. Okay, equals 0.99. What is the total system reliability? What would be the total system reliability? Okay. Given that the probability of the first event that to fail, okay, we have F1 if the first system fail and F2 if the second system fails. Okay. So to apply the rule of independence, we would say that the intersection between failing in the first server and the second server would equal to the probability, the multiplication of their individual probabilities, okay? And it will equal, in this case, 0.0001, okay? And here it's calculated the probability that they won't fail is 1 negative this, so is hello.